So we discuss about concrete, its properties. We are discussing about the fresh concrete, its properties, workability, segregation, and flowability, and bleeding, and which was related to workability. Then we discuss about the slump. We also discuss about compaction and vibration of fresh concrete. So these were the properties of the fresh concrete that we were discussing until the last lecture. In this lecture, we will be taking up the first property of hardened concrete, which is the mechanical property which has to do with the strength of concrete. So this is a property of a hardened concrete. Once the concrete hardens, once it is set, it begins to harden. And once it's in the process of hardening, it's achieving the strength at the same time. So right from its final setting time, when concrete has lost its plasticity and is now in a solid phase, in that phase, the concrete has started to harden and it has started to gain its strength. Now, strength of concrete, how do we measure strength, and how do we, first of all, what are the strength parameters? It's either compressive strength, one, or it is tensile strength, or it is the flexural strength, or it is shear strength, or it's torsional strength, or twisting strength. So these are the strength parameters on which basis we measure the strength of any material. Now for concrete, we can also go for measuring all these parameters of the mechanical properties of the strength. Related to these are modulus of elasticity, shear modulus, Poisson's ratio, and even in the torsional parameters, you can determine the twisting resistance and so on. So there are various parameters, and then there are sub parameters which we can determine for knowing the strength of any material. For concrete, there is a property of concrete which has to be noted down, that concrete has got a good compressive strength. It has got a good compressive strength, and it has got bad tensile strength. So when you push a concrete bar, concrete beam, or a concrete cube, or concrete slab, or concrete column which is under compression, it will behave good. Its behavior will be good under those circumstances. But when you're doing the reverse process, when you are pulling it, in that case, its behavior will be bad. It will not behave good. So rather, it will not behave. So it has been seen that the tensile strength of concrete is less than 10% of its compressive strength. If the compressive strength is, for example, 30 megapascals for concrete, its tensile strength will be even less than 3 megapascals tensile strength. So when we say that concrete is a good, it has got a good compressive strength, at the same time we say it's very bad in tensile strength properties. So based on these, we have the property of concrete is the flexural strength, like in the case of beams. Beam is, and you must have studied this already while you are studying the structural analysis. So it's under a flexural force, and under flexural force, the flexural resistance of the concrete beam, that is decided actually by its compressive strength. The flexural resistance is decided by its compressive strength. However, what we see that under flexure, what happens? There is always one side, the bottom side will be always under tension क्योंकि वो stretch हो रहा है, and the top side under bending or flexure will be under compression क्योंकि वो it's not stretching, it's actually being contracted, so it's under compression. So the flexural strength would be actually limited by the tensile strength and decided by the compression strength, limited by tensile strength for concrete. क्योंकि the concrete being weak in tension, bad in tension, weak in tension, it is liable to even under flexure or the bending, it's liable कि वो पहले tensile failure would happen on the bottom side of such beams. So it will fail first in tensile, resistance will be overcome, and it will fail in tension. So concrete has to be reinforced with steel, which provides the tensile strength. So steel being a metal, most of the metals have good tensile strength properties because they have a property of malleability and ductility both. So their tensile strengths are much better than the case of the concrete. Can any one of you tell me what is the tensile strength of mild steel? Have you heard about mild steel? Strength of concrete and that of steel. 3 compared to 250, that is almost negligible for concrete. So we usually provide steel within concrete to reinforce it, to give it its tensile properties or the tensile strength. Now that explains to you at this stage, that is enough for you to know that why do we provide steel within concrete. So what does the strength, any of the strengths, but we will be talking about the compressive strength basically of concrete at this stage, because that's the deciding factor for concrete. What does the strength of concrete depend on? It depends on main thing is water cement ratio, which I was discussing in the last lecture, where I gave an answer to one of the questions. So the strength, the compressive strength of concrete depends primarily on water cement ratio. It can depend on many other things. The strength can depend on age. It can depend on the age of concrete. What is the date from its casting? Is it 3 day old? Is it 7 day old? Is it 28 days old? It also depends on that. So the strength keeps on increasing with uh, until you are near 21 to 28 days, and then it might have reached almost the upper plateau of the strength, and after that the strength may keep on decreasing and deteriorating with time, but that process is a long process then over years. So the strength increases with age up till you have 28 days of concreting. Strength would also be dependent on various other things like porosity of the concrete itself, and it would be dependent on the strength of aggregates, and it would also depend on the texture or grading, shape, and size of aggregates. So these are the factors on which the compressive strength of concrete primarily it depends on water cement ratio. That's the first thing I'll be taking up. Just so I was saying that the strength depends on these parameters, and the primary parameter on which the strength depends is the water cement ratio. Now, when we say the water cement ratio, I have explained this to you last time that we actually mean the ratio of the water to the cement in terms of weight or in terms of a volume. It could be in terms of weight or it could be in terms of volume of the two materials. So we usually take it because water has got a density of around 1 on if it's pure water. So it would, without any added materials in it, so it would have a density of around 1. So it hardly makes any difference whether you take it in terms of weight or you take it in terms of volume. It would have made a difference if the density of water would have been greater or less than 1. So first the first equation in terms of the relationship between strength and water cement ratio is given by Abrams, the Duff Abram. The scientist name is Duff Abram. He gave this equation in 1919. It's known as the Abrams law. It's almost like a law that strength is proportional, inversely proportional to the water to cement ratio. It's inversely proportional to water to cement ratio. That means strength is here, and then on the other side, after the proportionality sign, I cannot write down the proportionality sign here, divided by 1. Proportionality sign is this, 1 divided by water cement ratio. So it's inversely proportional to water cement ratio. So where WC is the water cement ratio of the mix, and you have, now if you can take it in terms of the proper law, it is FC is equal to K1 by K1 by K2 raised power W by C. So K1 and K2 are both empirical constants. This is an empirical equation. So these are constants. So the value of K1 and K2 would depend on the other factors you have listed here. So they would be dependent on the other factors. So the constants always are meant to maintain the that you are taking some variables, and the variable here being W by C, it being the primary variable in this equation. So the empirical equation that you are getting here has got K1 and K2 as constants, which are actually dependent then on the other factors: age of the concrete, the porosity, the strength, texture, grading, shape, and size of aggregates. This is one form of equation given by Abrams. Then you have another by Rennie Ferret, who gave the equation earlier than Abrams in 1896, but no longer in being used. Its Fc is equal to K into C by C plus W plus A square. So here again, K is this in both. Fc was here the strength of concrete. This is strength or stress in concrete. This is strength of concrete. K is again a constant. Now these C, W, and A are the proportionality values with respect to the volume. So this is C is volumetric proportionality of cement, volumetric proportionality of cement. Volumetric proportional of cement, that is C. Then you have W, which is volumetric proportional of water, and you have A, which is volumetric proportional of air. So they are proportional with respect to each other, and it's a square equation, so it's a power equation here. So now when you draw a graph between the strength and water cement ratio, this is what you get. The main equation that you are getting is somewhat like this. This is strength Fc, and this is water cement ratio W by C. Now this type of equation, this red colored equation curve, which resembles an equation, an inverse proportional relationship between Fc and Wc, it is when it's fully compacted, when concrete is fully compacted. But when it's not fully compacted, it may be insufficiently compacted. And it's insufficiently compacted, but with vibrator used, but not full vibration has not been achieved. So the curve would first go like this and then come down like this. When it's hand compacted by a tamping rod or something, the curve would look like this. This is hand compacted. So when we say that there's a relationship between strength and water cement ratio, it's important to note down that it depends upon the amount of compaction at the same time. The amount of compaction. So when it's fully compacted, then its initial strength, even at low water cement ratio, is higher. But when it's not fully compacted, it's insufficiently compacted, resembled by the green lines here. Then initial strength at low water cement still is less. So when water cement ratio begins to increase, it then increases up to a stage and then again decreases with the increase further in the water cement ratio. Now, why does this happen? As we move in this topic, I'll be discussing this. Why does this happen? So at this stage, you remember that compaction has a effect on the strength. And if you're not compacting properly, even at low water cement ratio, you will not achieve a proper higher strength of concrete. Thereby, compaction is important in all situations. Now, there is a difference then between fully compacted here, this red line, and over compacted. अगर आप उसके से ज्यादा फिर compaction करना start करोगे, then segregation and bleeding tends to happen, and then again the strength begins to decrease. So there is a limit to the compaction as well, which is then called the fully compacted stage. You will all rejoin